Earlier today, the Nobel Prize in Physics for 2020 was announced, awarded for discoveries involving black holes, particularly for the discovery of a supermassive compact object, aka a black hole, at the center of our galaxy. This is one of the most interesting discoveries, I think, in the last century of physics, is that at the center of our galaxy, and probably at the center of every galaxy, is a supermassive black hole. It makes sense, right? That's where a lot of matter is going to end up, so it makes sense there would be enough matter to create a supermassive black hole there at the center of the galaxy. So what I wanted to share in this video is an activity that I've used for a couple of semesters about this black hole at the center of the galaxy. It makes for a great computational activity / take-home lab if you're in need of lab activities for students to be able to do remotely without any equipment. So what I'm going to do is include in the description below a link to this Trinket course page where you can use this activity. Feel free to use it with your students. Here, there's a page that has just a little introduction about gravitation. If you haven't covered it yet, this is a great way to introduce gravitation. If you have, it's a great application of it. So this page just reviews the gravitational force equation. There's a gravitational constant, mass of the one object, mass of the other object, divided by the distance squared, times the unit vector going from one to the other. And I think they've defined this r hat a little bit differently since there's no minus sign in front of here. The r hat is just defined so that it always is an attractive force. Then we come over here and we've got a video of evidence of the existence of this black hole at the center of our galaxy, because it's a logical question. How do you know this black hole is there? By definition, you can't see a black hole. Well, we can see it we can observe it based on the effect that it has on the stars around it. So this shows you the trajectory of several stars going around the center of the Milky Way galaxy. And what you'll find is that they are orbiting around something. Let's actually put this in slow motion here so you can see a little bit easier. So this one you can see makes a loop around here. Hard to tell if that's a closed orbit. I think it's going to be a closed orbit. But this one here makes this nice, neat ellipse that you can compare directly with the ellipses that you have in your textbook that happen with a gravitational orbit, right? So you have all these great data points here that are measured that make this nice ellipse. You can also get some information off of here, right? It's because you can watch the time of the orbit here, so you can measure how long it takes. So the orbit ends at about 2007, it looks like 2006.9. This is the year 2007 basically, and the orbit starts in 1990 something, 1994. So you can use that to get the period of the orbit going around. You can also get an idea for the scale, because this length scale here is 10 light days. You can convert that into meters, kilometers, light years, whatever your favorite units are there, and get both the period and the amplitude for this elliptical oscillation here. So you get that information down, the period of the orbit, and how wide is the ellipse at its widest point, how wide is the ellipse at its narrowest point. So you get those three pieces of information. Then you come over here to a handy GlowScript code. What this GlowScript code is going to do, let's go to full screen and bump up the font size a little bit. This is recreating that video here with an animation. So we have the black hole in the center. I've made it a gray hole instead, just so that we can see it. And then we have the star going around that black hole. It is making a nice complete revolution. It's not quite the same as the other one. It's a little bit short in terms of the orbital period, and the distance isn't quite right? It's not quite making that 10 light days. So what the students have to do is adjust the initial conditions. So there's a few initial conditions that they can adjust. They can move the star a little bit farther away from the black hole. The black hole is pinned down at 0, 0, 0. Think of that as the origin for our galaxy. So they can make it start farther away to give it a little bit more potential energy, or put a little bit closer to give it a little bit more negative potential energy. They can change the velocity vector, right? They can make it go faster in the horizontal direction there. They can make it go slower in the horizontal, or they can give it a little bit of a push in the vertical direction. In principle, you only need to give it a position in one direction and a velocity in the other, so that you don't have those mixing in terms of how they influence the trajectory. It's just a little bit easier to do it that way. Another condition the students can adjust is the mass of the black hole. And a particularly clever thing to do is to just look up the mass of this black hole. I'm sure it's in the Nobel article somewhere, because then you know what that information is, and then you just need to adjust the position and velocity initial conditions. And so even if you don't talk to your students about the rest of the code, if you just leave the rest of that as a black box to them, this is a great activity because it gives the students an idea of how important this computational modeling is, because this is how we determine what the mass is of the black hole at the center of the galaxy, or at least as one of the tests we can use. But it's simulations like this that allow us to find out these things, because obviously we're not going to the center of the galaxy anytime soon to put the black hole on a scale. That doesn't even work in space, let alone the ridiculous amount of time it would take us to get to the center of the galaxy. And so it both highlights to students the importance of computational modeling and gives them some confidence in these wild numbers that they'll be seeing in this article about the mass of the supermassive black hole, how far away it is from the nearest star, etc. If you want to go over the nuts and bolts of the simulation with your students, you get to talk about how the gravitational force is calculated using this g-force function. I'll have a video with more detail about that. Add a link in the description below. Basically, we set the universal gravitational constant. We calculate a distance vector going from the star to the black hole, so it's always going to point inward. Then we calculate the magnitude of the force based on the equation we just had on the screen a couple minutes ago. Then we calculate the unit vector that's going to point from the star into the black hole, and then the force vector is just the magnitude times the unit vector. Magnitude and direction right there to talk with your students about vectors. Then we go and use that force to update the velocity. So this is just the change in velocity is the force divided by the mass times the time step. And then we update the position. The change in the position is the velocity times the time step. These are equations that you use in a high school physics class. They are accessible to students of any mathematical preparation. So any student can study this animation of this sun going around the black hole at the center of the galaxy. You can also use this code to talk about Newton's third law, because we have the star moving and we have the black hole moving. But you'll notice, of course, in the animation that the black hole doesn't seem to move too terribly much because it's so much more massive than the star. So you can also talk about momentum, about how they have the same change in momentum, even though they've got a different change in velocity, because one of them has such a greater mass than the other one. So I hope that's useful to you. If you are a physics educator, you can use this in your class. If you're not a physics educator and you just want to learn more about this problem and play around and get a little bit of experience with this, you can grab this code and play around with it till you get the size of the ellipse and the period of the orbit correct. So congratulations to the winners of this year's Nobel Prize. Looking forward to getting to talk about black holes with folks in the coming weeks.